secret to winning the pool is just pick teams that start with K. The winner won it last year by picking teams that started with K. It's true. She was just like, she didn't even know she won this one. All right, so Thursday I asked you guys to do a little bit of reading over the weekend to find an article of interest to you where the authors have used the ANOVA. And I asked you to come prepared to come and discuss the article. And the idea of these kinds of exercises is to learn how ANOVA is being used in your particular area of interest. And the other thing to think about when reading and reviewing these articles is what is the, not only how are they being used, but are authors thinking about what it is that they're doing with these models, and is there any evidence to suggest that in the articles? So do they talk about assumptions or anything? So who'd like to share that?
I mean, I have an article. There was really nothing discussed, so I have very little time to say it.
Well, that's actually speaking volumes, though, isn't it?
Volumes about the article named Volume-Related Differences in Emergency Department Performance. So this article was basically doing a retrospective analysis of this survey data they have, the Emergency Department Benchmarking Alliance survey, in which they collect a whole host of information about kind of performance measures and size of emergency department and trying to figure out kind of how busy emergency departments are. And they were trying to figure out what the, basically what the correlation was between how busy emergency departments are and how well they do on performance measures. So as they tell us, so they basically, the performance metrics, they had two primary outcome measures of performance. One was length of stay and one was left without treatment complete for patients. And they say we used, in fact, it was interesting, they refer to the central limit theorem, but they say we used descriptive statistics to summarize operating characteristics, utilization rates, and performance metrics across the 5 volume bands. So they basically broke the volume into 5 different bands, which were under 20,000, 20 to 40, 40 to 60, 60 to 80, and over 80. They said the data were in aggregate, and they aggregated patient, some data that they had over individual ED patients within kind of overall ED. So all their data were at the level of the ED. Because they said because of the large number of cases within each ED and using this central limit theorem, the observed ED operating characteristics, utilization rates, and performance metrics were assumed to be approximately normally distributed. ANOVA was used to compare the differences in operating characteristics, utilization rates, and performance metrics across the volume bands. And then linear regression analysis using linear, quadratic, and lowest smooth line fit was used to evaluate the correlation of ED length of stay with census category. Univariate logistic regression was used to assess association between left without treatment complete and door to physician time at different volumes, and odds ratios with corresponding 95% confidence intervals were calculated and reported. So they give the results in table 3 of the 5 ED volume bands, and looking at differences in operating characteristics, utilization rates, and performance metrics, may report a whole host of significant differences.
Any mention of adjusting for multiple comparisons or just the results of regression or something like that?
Not that I found. When I looked at some other times you say. No, that was basically, let me just give the results. There was pretty much no discussion of that.
What do you mean by adjusting for multiple comparisons?
So she said that they reported a whole bunch of p-values, right?
Right.
And on last Tuesday we talked about, I think it was last Tuesday, we talked about why we use ANOVA.
Right.
We want to use the ANOVA. Why do we want to use the ANOVA? Or when would it be appropriate to use ANOVA?
When you have more than
2 or more groups, right? But remember we also wrote down the null hypothesis for the ANOVA? It says that all of the means are equal.
Right.
All right, so the reason that we do the ANOVA is that we want to protect ourselves from an inflated alpha rate, right? So if you do, with survey data, you can do a gazillion t-tests or a gazillion ANOVAs or 100 hypothesis tests. And I'm going to draw a graph for you as to what happens if you don't, to your family-wise alpha, if you don't adjust for these multiple comparisons, these multiple hypotheses that are tested.
Okay.
Right? So some people are very easily seduced by lots and lots of small p-values. Has anybody ever read an article? There's an article by a guy, I don't remember his name, he's got a Greek name. It was published in like 2005.
Oh, Ioannidis.
Ioannidis.
Yeah.
Have you all read that article? You should, I'll get the article and post it on Blackboard. Most research that you read is wrong. I'll post a link to it out there, out on Blackboard for you. It's a good read. It's a very good read. It's a very good read. Okay, all right.
Why most published research findings are false?
Right. Regardless if it's from industry, academia, or government.
So they reported 16 p-values and 12 of them were significant.
Right. I'm not surprised. Right? Okay, all right. So let's talk about some of the things in that particular article, okay? Have you guys ever heard of median splits? You're going to take a group, split it at the median, and compare one group versus another. That happens a lot in medicine in particular, right? But here's what I want to talk about here for a second, is this artificial categories, right? So in the article that we just heard about, they had this nice continuous variable. Was it like census volume?
Volume, yeah.
Admission volume or something like that? Okay, so admission volume, so let's see if we can draw that. And let's see if we can think through the potential problems of having these artificial categories, all right? So on our x-axis here, we're going to have what? Admission volume. And on our y-axis, we're going to have, what, like success, treatment success, or something like that. Or number of successful treatments, or something like that, right? Some outcome, right? And what they did was, let's say that the curve looked something like that. I don't know what it looked like. Did the authors actually even tell you? Did they plot the curve?
They didn't plot the curve. We have a table, and they do say, so table 1 displays breakdown of participating EDs by annual volume and as a percentage of total membership. Although the breakdown of EDs in a volume bands of 20,000 annual visits, like the other survey data, is based on self-report. We've used this breakdown from the first surveys because it's thought by members makes sense operationally and functionally. In 2009, the median ED annual volume hovered at 40,000 visits, offering a natural breakpoint for the 5 EDBA volume.
Okay, all right. Again, with the median breakpoint again, all right. So let's say that we have data that look like this, right? And what it sounds like is that the authors took those data and came up with 5 categories. 3, 4, 5. And then they said they grouped these people like this, right? So the assumption here is that everybody that they grouped in group 1 here, that they collapsed into group 1, that the relationship, that all of these guys had more or less the same level of treatment successes, the same number of treatment successes. What are your reactions to that? Oh, everybody does it, right? Retrorectal validity, right? What do you think? That's the implicit assumption, right? That whether or not that's the implicit assumption of the model, is that these people are more or less the same. What do you think? Reasonable assumption? Probably not. what happened, this is just a nice, I mean, if they didn't do the ANOVA and they did linear modeling, and it sounds like they did, you know, all that quadratic and cubic and all that stuff, you guys know how to do that. That would be taking volume and success, not categorizing and adding squares and cubes into the linear regression, right? That would be, so instead of this, it would look like this. Right, the x's haven't changed, I've just squared one of them. And now I'll give you my
I think it's like, the nice part about doing the upper strategy is that they blind themselves to like outliers, so they don't have to deal with that, even though that's wrong. But then,
well, even though it's wrong.
Yeah, even though it's wrong. But then, the hard part about this that I feel when I'm like evaluating stuff is like then it feels like I'm looking at my data and then deciding what it looks like, and then I'm modeling. Whereas like a priori, you had told us like the way to think about this is to basically conceptualize a model. So I conceptualize my model, I have all these factors, and then I go look at the data, and then I notice that they're like curved this way or curved that way, and then I start adjusting for it, and then it feels like I'm still adjusting for things
That you already know. So there's a difference here between testing a hypothesis and trying to model the data, right? Something to think about here, because these splits, these artificial categories happen all the time. You've heard of non-parametric statistics, right? So you've heard of, well, you've heard of the Pearson product moment correlation coefficient, right? So so here's, if I were to take two variables, like, I don't know, give me two nice continuous variables. Age, and weight. Okay. So both of these variables are nice and continuous, and let's say that the relationship looks something like that, right? What many times people will do is they'll then take the age variable and they'll have old and young. And sometimes they'll arbitrarily say 65 plus is old and less than 65 is young. Where'd that number come from? Medicare, and that's changing. It's more or less arbitrary. Okay. And then we'll have weight, and then we'll have something like not obese, based on BMI or something like that, and that number is going down over time, right? And they'll have these artificial dichotomies here. So we know, so if I were to correlate weight and age without doing anything to the data, I would get a nice Pearson product moment correlation coefficient, right? But if I artificially dichotomize these variables, I get what's called a tetrachoric correlation. It doesn't matter. I get what's called a tetrachoric correlation. And we know that studying the properties of doing these artificial dichotomies, is that we know that when we do these dichotomies, on average, the association between our variables will be on average about 20% higher than they would be had we left the data in its natural state. What do you think about that? It's systematically higher. Systematically different means what? When we say the word systematically different in this case, we're referring to bias. We're referring to bias.
I think we read an article in Journal Club like a month ago that was they analyzed the data both ways, like using vitamin D level continuous, or then if they categorized it arbitrarily to where the breakpoint in their data was, and then they sort of published like high, low vitamin D makes a difference. So.
Now, in the past, there are strategies for dealing with data, right? There are strategies for dealing with data where, I don't know, let's say that the data look like that. So, age and prevalence of some condition. Maybe it's not linear. Maybe it really looks like that, right? So what am I going to do? Artificially, see, what I could do is something that's referred to as a mixture model, is I could make the assumption that underneath this curve, there's really two populations, right? And then I could say, well, if you're at this arbitrary cut point here, then you're in that group, and if you're at that cut point, you're in that group, right? But you see the two curves overlap, and this is just a probabilistic model. So there are ways of doing that. Right? Or what I could do is I can actually model the relationship between these things using something like calculus, and I could come up with inflection points, right, on this curve here. Something like that. And I might be able to categorize and do what's called a piecewise regression. Piecewise regression, or it's often called hockey stick regression. A lot of times we see lots of processes in nature that look like that. Have you ever done clinical trials? This is what enrollment looks like in studies. So here's time, and here's enrollment. This is just what happens because we're lazy people. But a lot of things in nature look like this too. So what we might be able to do is model this relationship too. Where when we make these dichotomies or these splits, there's some empirical basis upon which to make this split, as opposed to just doing quintile splits. And we'll do quintiles because 5 is a nice number. Does it make sense? Why did you choose these breakpoints? Right? Okay. Things to think about when you're reading these articles. Because the implicit assumption here is, well, here I would look at the relationship, the people in this group. The assumption here, more or less, is that the relationship between age and prevalence is fairly similar. And in a regression sense, it is similar. So I could fit a regression line here, another regression line here, a regression line here, a regression line here, and a regression line there. Right? Things to think about when you're looking at the literature. And remember, the reason that we do science, the reason that we do studies, is to make inferences from our sample to the population. And the assumptions, whether or not they're implicit or explicit, should affect the inferences that you're making. Right? Things to think about. Did anybody else have an article? An interesting article? We'll deal with this family-wise error thing in a little bit. No other articles? Pardon? Second?
Articles just not
No, some of the fact that they didn't do a whole lot of stuff, to me, says a lot.
I feel like they don't explain, like in a lot of these articles, there's like another aim besides the ANOVA, so they don't always explain, like, they just say, like, we did an ANOVA and we used a P level of, 0.05. Like, they don't really get into, like, their assumptions and stuff. But
one thing I hope that you're realizing is that it's all these, like the model is based on the assumptions. So if you don't talk about the assumptions, then really how can you think about the quality of the information, the evidence? Really, this is what we're talking about, quality of evidence, right? What's the quality of the evidence? Right, does that make sense? Quality of the evidence. Okay.
Can I just bring up a study and ask you
Sure. Let's
whether,
talk about studies.
whether this makes sense to do? So there's this article of survey data about geographic variation in practice patterns, I'll just use it generically. And they surveyed physicians and then grouped them in different ways, first by U.S. Census, geographic region, and then by managed care organization penetration rate.
Within the region?
Yeah,
Okay.
like nesting it, I guess. And then also by metropolitan statistical area, which I don't know. So like,
So that would be a census region. They did it further?
yeah, U.S. Census region, metropolitan statistic area, and managed care organization penetration rate, those three things.
That's odd, but okay. You guys understand, like I said, there are what, 5 census regions. Within that, there are 9 or 13 sub-census regions. Within sub-census regions, there are MSA stands for metropolitan statistical area. So
Metropolitan statistical areas are larger than census areas.
then what?
They're larger than census areas.
You sure about that?
There are 9 census regions.
I'm pretty sure.
They're
show
really
that.
sure.
They're small.
Which MSAs are smaller
I
than
thought
census
MSAs
regions?
cover a wider tract.
Anyway, the point is,
Anyway, so then the point is that they then felt that I'll just read you this text and see if it makes sense. Because many advanced statistical methods require independence of observations, correlation analysis was used to determine whether an individual's response then they surveyed them over 2 years, whether response for year 1 for one practice pattern was independent from their same response for year 2. Similarly, correlation analysis was used to determine whether an individual's response was, so they like had all these different levels like between person.
so this is a mixed model that we were referring to before.
All kinds of craziness. They decide that repeated measures analysis of variance is the appropriate method to look at like those different geographic regions.
Taking into account, all right, so let's think about it. This actually sounds like a
So what is that?
reasonably thought out article. Okay, so remember we did talk about this before. We talked about, remember we came up with the topology. We had the concept of visits nested within patients nested within providers nested within facility, and so on and so forth. We sort of built this topology, this hierarchy, right? So in this sense, can we do ANOVA and regression with these data? Yeah, right, but what they did was a repeated measures ANOVA, and they explicitly acknowledged, or at least tested, it sounds like they acknowledged in some way, the lack of independence of observation from year 1 to year 2, right? So they were thoughtful about it. Kudos to them. Good to them. And then in which case they can take into account the lack of independence between the observation. Now we haven't learned those methods yet, but we're building up to it, right? But it sounds reasonable, what they were doing, right? But at least they were talking about it, they explained what they did, they let you know what their assumptions were. That's really good stuff. We don't see that a lot. Okay. Should we jump back into the code? Back into the code? Okay. So here's what I'd like to do today. Let's finish up the analysis that we were doing on Thursday. And then I'm going to give you a choice. And the choice will be yours, and I won't take offense to either decision that you would make. So what I would like to give you the choice of reanalyzing the data set that we have here by hand, because I only think there's 12 observations, to give you a sense of what the ANOVA is doing. Or I have another handout that everybody should have gotten. There were copies of it going around. Or what I want to do is I want to start going into using regression to do ANOVA, to answer very specific kinds of questions. And when we start getting into things called contrast matrices, you'll begin to, it becomes more concrete when I start talking about things like asking very specific questions of the data and taking into account the properties of the data or the properties that you assume the data have. Okay? So if you recall from last time, the data set that we were dealing with had to do with the comparison of 3 treatment conditions. So we had treatment A, treatment B, and placebo, and what we were interested in doing is we were interested in looking at the relative effect of each of these drugs on time to, or number of days it took to heal, right? And we started off our analyses by, like we always do, by doing some exploratory work to be able to look at, well, with respect to the ANOVA, because it's a correlation, one thing that we're going to be interested in doing is we're going to be looking to answer the question, do we have homoscedasticity, so we can easily look at the variances, the standard deviations between the groups there. And we sort of came up with a rule of thumb that what we're going to do is we're going to take the standard deviation of the group that has the largest standard deviation, and then we're going to divide the smallest standard deviations into the largest standard deviation, right? And if the largest standard deviation is, say, more than 2 times or greater than 2 times the variance of the smallest group, then we might have a problem with heteroscedasticity, right? It's a rule of thumb, right? Now here's something to know, is that when you have very large samples, a lot of these assumptions that we've been talking about, you can ignore. The F statistic, the ANOVA, the general linear model, is very robust to departures of their assumptions.
What's large?
30. No, like hundreds. Actually, for the kinds of data that you guys would deal with here, like a claims type data or survey type data where you have tens of thousands of observations, that you can ignore. You can actually do logistic or binary outcomes, logistic regression, or look at proportions with a general linear model, and you should be relatively safe. There are a couple of epi papers that have been written on this stuff, on the robustness. We're talking about the robustness of the general linear model. The only assumption that the general linear model is not robust to is the independence of the error assumption. So you can have departures of normality. You can have unequal variance. And particularly, you can have wildly unequal variances if you have a balanced model. So we refer to a balanced model as having equal number of people in our groups. Something to keep in mind. But when you have small studies like this, with only, say, 25 people in it, then these assumptions become important. Okay. And then we did our box plots. Right? Right? This is another way of sort of eyeballing the variance of the data. Right? We don't see any outliers, right? Because if we saw little circles outside the whiskers, we might have some outliers here. And we know now that we've talked about regression, we've talked about the influence of an outlier. The influence of an outlier. And we now know that influence has a statistical meaning. And then, actually, before we do the ANOVA, it's probably a good idea to write down our statistical model. Right, so we remember what the ANOVA is actually testing. So who can help me write down what the statistical model is? Right? So the null hypothesis would be mu1, in this case mu2, equal mu3. And if we wanted to write this generically, you could write it like that. Okay. All right, so that's the ANOVA. That's the null hypothesis for the ANOVA. So to do the ANOVA in Stata, it's like it couldn't be any more easy. It's just ANOVA, your dependent variable, and your, what is this called in the ANOVA? What's an independent variable called?
Factor.
A factor. Right? Factors have one-to-many levels. Good. Okay, all right. So here we have our ANOVA table. This is one way of doing it. We have our treatment and our residual. Treatment is going to be the name of our factor here, right? Residual is another name for what? Error, right? So for the ANOVA table, we generally think about between groups error and within groups error. All right? Between group variance and within group variance. Make sense? Okay. So these are, oh, here we go again, partial sums of squares. Partial, there's that word again. Sums of squares, and these are, you know how to do these. We'll do this, like, if you want to, we can do this one by hand, and we'll figure out how to calculate these things. And then when we talk about the analysis of variance, you'll see how this really is variance. It's all variance. The degrees of freedom right here, so the degrees of freedom for between groups is going to be k minus 1. So however many levels you have, minus 1. Right? And then we have residual or within group degrees of freedom. That's going to be capital N minus K. Capital N is the total number of observations in your data set minus the number of groups. And then we have the total degrees of freedom, which is going to be capital N minus 1. Okay. Sums of squares, you know how to do this. These we'll do together. And then mean squared is the sums of squares divided by degrees of freedom. You've seen that before, right? Sums of squares divided by degrees of freedom, you know to be what? Variance. In ANOVA, it's referred to as the mean square. And then we have this F statistic. It's not a curse word, despite my propensity to swear. This is our F statistic. This is what we refer to as our test statistic for the ANOVA, the F statistic. And the F statistic is the ratio of the treatment variance to the error variance. So I'm going to divide my treatment variance by my error variance to get my F statistic. It's a ratio of signal to noise. How much variability is there between groups? How much variability is there between groups relative to the variability within a group, right? And if you think about it in terms of a model, right? And again, we like to write that. Oh, I like to write that model because it helps me think about what exactly it is I'm doing. So how much difference is there between groups relative to differences within the group? So if I'm in group J, my expectation is that everybody in group J will have the same mean, right? So any variability within the group is due to stuff that's not in my model. I haven't accounted for that variability within a group. That make sense? All right, okay. And then we have this p-value based on the magnitude of our F statistic and the F distribution based on these degrees of freedom. Right? So just like there are an infinite number of t distributions, and what distinguishes one t distribution from another t distribution? Degrees of freedom. Thank you. Which came in just in time for that. There are actually, in some sense, more infinite number of F distributions, because the F family of F distributions takes two parameters. It takes on the numerator degrees of freedom and the denominator degrees of freedom. Right? So let's look at this here, all right? So we know that our F statistic is statistically significant at, it's less than our sacred cow of 0.05, right? And the other thing that we know from our model is that we get an R squared of about 37, which actually I'm more impressed with this than I am with this. Right? So what can we say at this point? And remember, this was a randomized clinical trial. So the fact that we have a statistically significant effect actually allows us to make a very powerful statement or make a powerful inference regarding the relationship between treatment and our outcome here.
One of the groups is different.
I'm sorry?
That one of the groups is different.
There's at least one pairwise difference, right? Okay. What else can we say based on what we see on this table here? So remember way back when we talked about 3 things necessary to establish a causal relationship? You guys remember what those 3 things were? The first thing is that we need to have temporal order, right? That means the cause has to come before the effect, right? At least in this instance of this universe, the quantum physicists won't disagree with that, right? But in this instance of this universe, cause has to come before the effects. Have we satisfied that criteria by giving treatment, then measuring the outcome? Okay, so we've satisfied that criteria for establishing the causal relationship. Does anybody remember the second ingredient for establishing a causal relationship? Covariance. Covariance, right? And that's what this tests. Does the treatment and outcome systematically vary with each other? And this is evidence, this is statistical evidence that suggests, yes, they do. They do. So have we satisfied the second criteria for establishing this causal relationship? We have statistical evidence to support that inference, right? This is all about inference. What's the third thing that we need to establish, we need to do to establish a causal relationship?
Rule out an alternative explanation.
We need to rule out alternative explanations. And because this is a randomized clinical trial, can we make the assumption that we've ruled out alternative explanations? Yeah, we can. Yes, we can. So now, because we've satisfied those criteria, at least for this study, we can make very strong statements. Right? Can we look at this value here, this 37, and say, these data suggest that treatment is responsible, as opposed to simply saying is associated with. Treatment, what drug you receive, affects approximately 37% of the variability in the outcome. Yeah, we can make that strong statement, but notice I also included that goofy language of these data suggest. But instead of just saying is associated with, now I can make a stronger statement and say, you know, accounts for, is responsible for, leads to. Right? That's a much stronger statement than just saying that they're related to each other. Okay? So looking at this p-value, this simply says that there's at least one, these data suggest, the ANOVA suggests that there's at least one pairwise difference. Okay? Does the ANOVA tell us which of the at least one pairwise difference there is? No, it doesn't tell us that. But what it in some sense does is it sort of gives us a green light to peek under the covers and say, you know, okay, where are those differences? Fair enough? Okay. So the reason that we want to do an ANOVA as opposed to 3, how many t-tests could we do if we have 3 groups? Remember we wrote that down before? If there are k levels, I can do k minus 1 divided by 2 pairwise comparisons. So that would give us 3 times 2 is 6, divided by 2 is 3. 3 pairwise comparisons. So if I didn't do the ANOVA, I could possibly, if I were to look at each t-test at the 0.05 level, if I were to look at each t-test at the 0.05 level, my family-wise alpha rate would not be 5%. It would be approximately, it would be a little bit, it'd be about 14%. Right? So what I did was I did 1 minus alpha raised to the c. So alpha is your probability of your type 1 error that you want, and c is going to be the number of comparisons that you're going to do. So this comes to be about 14%. Or you guys have heard about the Bonferroni correction, right? So the reason that this goes, I know this is about 14%, or most people would write about 15%, is because this curve looks like this, and I'll show it to you. And then what Bonferroni did was he says, well, all I'm going to do is I'm going to take my alpha and divide it by my number of comparisons. It's a quick and dirty back of the envelope calculation. C is the number of comparisons that you're doing. So whatever 0.05 divided by 3, what's that going to be? 1.012 or something like that? Something like that. So what I would do is I could do 3 t-tests, but instead of rejecting the hypothesis, each of those t-test hypotheses at 0.05, I'd have to reject it if and only if the p-value were less than 0.015 or whatever 0.05 divided by 3 is. But even though the p-value would be less than 0.015 or whatever that is, I can't say that I'm rejecting it at the 0.015 level. I'm still rejecting it at the 0.05 level.
So are you supposed to always use that Bonferroni correction? Or do people, is it assumed you're using it? Because I feel like I've never seen it written out, and so is it like implicit that you're using it if you're doing an ANOVA, or no? Okay. So people just...
Paper like Kristen just said, so they put 16 p-values, no mention of any corrections.
Okay.
Yeah.
But you're supposed to use it when in that situation where you're... Okay.
Well, it's not like they're going to lock you up. What I'm trying to convey, to communicate...
Police.
Yeah, right? What I'm trying to communicate to you is what are the potential problems with not adjusting for these multiple comparisons. So this gets back again to inference. So let's say one of those 3 p-values for the t-test was 0.04, right? You'd be like, yay, I get to reject the null hypothesis and publish. When in fact, that p-value probably isn't statistically significant. So your inference, the validity of that inference saying that these 2 things are related would be improper. Or could be improper.
So when you do the correction in Stata, does it give you the p-value at the 0.05 level and the level that...
Now what it's going, so there are a couple of strategies I can do, right? I could do 3 t-tests. And that's easy, and it'll give me the unadjusted p-values. I would then say, well, I'm going to do a Bonferroni correction, figure out what 0.05 less than divided by 3 is, and see if my p-value is less than that new alpha, right? What the software will do for you is it will give you what we refer to as adjusted p-values. If you say, okay, after my ANOVA, use this method for these post hoc comparisons.
Okay, so it gives you both.
No.
It gives you the ANOVA table, and then after that it gives you the
adjusted p-values,
yeah, okay.
the corrected p-values. So that's what I want to talk about next, right? There are lots of different ways that we can, there are lots of different methods for adjusting for these multiple comparisons, right? And let's talk, I'm going to write down a couple of them. But they're all aimed, their purpose is, they all have the same purpose, right? One is called the Tukey test. Notice there's no R. The Tukey test. There's a method called Chef-A. There's a SIDAC test. These are named after people, the people who developed these things. There's the Bonferroni. There's the, well, this one's not named after a person. It's actually Fisher's LSD. Fisher, it has nothing to do with lysergic acid. This stands for least significant difference. This is fun to write about, or you can crack jokes. There's something called Dunnett's test. You can fill volumes of procedures for adjusting for multiple comparisons. One thing I like, another method, there's another method called a step-down test, which we'll talk about in a minute. Right? So the other thing that we want to talk about are differences between post hoc comparisons and planned comparisons. Right? So post hoc means, sort of after the fact. All right, so when you go into a study and you don't know very much about the area in which you're studying, in this case here we have treatment A, treatment B, and placebo, right? And say this is the first time we've ever studied these things. These are candidate drug compounds, and we want to compare it against nothing, right? That's a pretty reasonable test to see, does this thing work? When we talk about efficacy, we have to ask the question, as compared to what? Right? We talked about that. Remember, It's a Wonderful Life and A Christmas Carol? We did that one? Okay, all right. So if I don't know anything about, or don't have an opinion, a strong opinion either way about what treatment might be superior, I might go in and do all possible pairwise comparisons. I have no real propensity one way or another to believe one thing is superior to another. So what I would do is I would do all possible pairwise comparisons, a post hoc test. Now when you do these post hoc tests, you pay a penalty, a statistical penalty, for not being thoughtful, or not knowing much about the world, or not having a strong belief about the world. So these post hoc tests, the ones that I've written down on the board there, on the left, they're conservative. They're conservative. Some tests, some of these procedures are more conservative than others. So in the sense of conservative, I mean, some of these tests, take the Chef's test, for example, makes it very difficult to reject any pairwise comparison. Even though I have a statistically significant F statistic, it is possible that when I do my post hoc comparisons, that every once in a while, maybe twice in a career, you might find a data set where you will not find statistically significant pairwise comparisons after adjusting for multiple comparisons. Right?
So why would anybody use that? Why would anybody use that one?
Because they're conservative. Science, by its nature, is very conservative.
But I guess is there, like if you're thinking about doing this, is there a reason to use one of those over another one?
No, not
Or
really.
does it just not-
Not really. I mean, in my opinion, no. For example, I would never use Chef's test. That's not true. I've used it once in my career. I used Chef's test because I knew I had to satisfy reviewers. Right? So the Chef's test, out of all of these things that we've listed here, this is the most conservative. So I used this when I had an enormous sample size, like something like 100,000 participants in my study. And I did something like 60 hypothesis tests. Now with 100,000 observations, the slightest difference between two groups is going to be statistically significant. So my rationale for choosing Chef's was,
You really wanted to find out.
well, I knew the study was completely overpowered. So I wanted to be very conservative. I personally, when I do my professional work, I'm not impressed by p-values. I'm impressed by semi-partial R-squares. That's what I'm impressed with. So, but I knew I had to put this out in mainstream journals, so this is what I did. And when I wrote about it, I wrote that Chef was chosen as it is the most conservative post hoc test. and I chose this because we had 100,000 observations and 60-something comparisons that I wanted to do. All right. I like to use Tukey's test. If you use Tukey's test, people aren't going to throw rocks at you. Right. Now, Tukey's test assumes that you have a balanced design, but if you don't have a balanced design, it becomes the Tukey blah 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 test. Somebody took the Tukey's test and generalized it to the case where you don't have an equal sample size, but you can still call it Tukey's test because it's Tukey's test. All right? Okay. All right.
Tim?
Yes.
All of these, multiple comparisons adjustments, are they meant to be applied when you're making just sort of univariate, pairwise comparisons, or say somebody runs a regression and they plug in, they have 15 independent variables, and one of them, lo and behold, is statistically significant.
That's a great question.
Should they be
That's a great question.
applying those methods?
So let's talk. That's a great question, and the answer is I don't know. So let's talk about that for a second. Does everyone understand the question? So let me rephrase it a little bit and see if I can. If I'm saying it a little different, but the spirit in what you're saying. So here we're talking about doing an ANOVA, where I'm trying to test a hypothesis. Are there group mean differences, right? Whereas in a regression model, I could have any combination of continuous variables and group variables. And I might fit a model. I might not be necessarily interested in testing a hypothesis, is this group different from this group? But I might want to be able to ask the question, holding these other variables constant, is the relationship between height and weight statistically significant? But because I have all of these other things in the model, technically, I have done 15 hypothesis tests. Should I apply some form of correction for those comparisons? Well, it depends on who you talk to in their training. Economists, for example, ignore these post hoc, this multiple comparison issue. They simply look at the individual p-values for the individual parameter estimates. Whereas if you're a trialist, clinical trialist, and you're testing a hypothesis, then you're going to, the agency, the FDA, for example, is going to force you to take into account the multiple comparison problem. Personally, if I'm going to use regression, I'm going to be adjusting for the multiple comparisons because I understand what's going on about testing this hypothesis and this and this and this and this and this and this. There's a lot of stuff going on, and I need to take into account the fact that there's a lot of stuff going on. So there's no correct answer. I think there are some answers better than others, but that's a matter of opinion.
Right. But these same methods could be potentially applied to an analysis of regression.
Yes. Yeah. Yep. Okay. Did you have a question?
No.
That was your question. Okay. Yeah. So, for example, what we could do is what's referred to as an ANCOVA, which is a mixture of ANOVA and it's an ANOVA, but you want to control for a quantitative variable, a continuous variable, or you want to control for something else, which could be continuous or discrete. You could still do a post hoc comparison on your treatment variable. Yes, you can do that. When I have a continuous variable, like age and weight, taking into account all these other things, in that case, there's like Tukey's, Bonferroni's, Chaffe's. That doesn't make sense because these methods were explicitly developed to compare differences between categories. So in the case of regression, where I have a continuous parameter, I might look at Bonferroni's, for example. Okay.
So if you do your ANOVA and the F statistically not significant? Is it?
You're done.
You're done.
You're done. Do not show, you shall not pass. That being said, that's a great question. That being said, I would still interpret this. I would interpret this because your F statistic could not be significant for a number of reasons. Usually if we're going to do a study, there's some pretty good, at least anecdotal evidence or some strong belief, or at least hope, that your intervention, your new intervention, has some effect. But we do the studies to provide the empirical evidence. Now let's say, for example, that you're in the lab and you develop some new compound and you don't have a whole lot of money. Are you going to go out and take a big chance and spend $5 million? So you're going to max out, you're going to remortgage your house, you're going to do your credit cards, and you really don't have a lot of money to do a properly powered study? No. What you could do is a smaller study as a proof of concept. You know you're going to get a large p-value, but what's really you're going to be interested in that case is the R squared, right? Which is why I'm interested in things like this as opposed to this. The fact that I have such a small p-value with only 25 observations is because the R squared is so large. Okay. All right, and we also showed another way to do it. This is just for the one-way ANOVA. There's a command one-way. This actually does a statistical test for the equal variance assumption. You can ignore this, right? You can ignore that. Okay, so Stata has these things called post-estimation commands. So one of the things, and this is a fairly new thing that they've added to Stata, which a lot of people are really happy about, is that we can get what are called marginals, right? Marginal commands. So the idea here is, has anyone ever heard of a least square mean? Yeah, a least, does anybody know what that is? No, a lot of people don't because it's a fabrication of SAS. SAS created this concept of what we refer to as a least square mean, or an LS mean. So let's say in my model that I had something like this. Right, so here's my treatment variable, and here's some covariate, some continuous covariate, right? Let's say that this is treatment, yes, no, and the covariate is like age. How old were you at the entrance of the study, right? So this means that everybody in the group, in group 1, right, would have the effect, their predicted value, y, would have the effect of being in group 1, plus some additive effect of their age. Now, if everybody is not of the same age, then what happens? Yij is going to be different for everybody within that group, right? Right? So how do we then compare one group versus another? Right? How do we compare group means between one group versus another after we have covariate at the effect of age or whatever the case may be? What we can do is we can say, okay, what is the expected value, this is E, expected value of Yij given age, the mean of age? So what will happen is we'll say, okay, I'm going to hold x2 constant. At what value am I going to hold it constant? A reasonable place to hold x2 constant would be at its mean. Not the mean for each group, but the overall mean of age. That make sense? Yes, no? Yeah? That's a least square mean. So how do we get these least square means in Stata? We're going to use the margin commands. So here are the means, the least square means from our model, right? And they include confidence interval, which is all well and good. And oftentimes in clinical trials, for example, you will see a plot that looks like that. All right, so here are the means for each of these groups based on the statistical model and their confidence intervals. So oftentimes you'll see a plot like this. Okay, so let's get to these post hoc comparisons.
Could you go back to the margins, the right before the graph?
The output, yeah.
And could you go through in words what the margin values?
Okay, so when we talk about marginal values or their predicted values, so actually what's going on underneath the ANOVA is really regression. It's really regression. So what it's going to do is it's going to plug in zeros and ones or something to your model to come up with an expected value of y. So these values, these marginal values, are the expected values of y based on the true underlying regression model.
Why do we do this for? Why do we do this?
So this is, let's say I wanted to include a covariate, for example. There isn't a single expected value of yj, like the expected value of some person in group J, because in the case where we have a covariate, each expected value will be conditional on this person's age because it's in the model. So how do we take into account the fact that everybody in group J is allowed to have a different expected value? I can condition out, I can hold age constant. And when we talk about models, if I were to guess somebody's age, their best guess for age would be? Average age. You plug the average age into the model for x2 here, and then get the expected value of y. What is the expected value of group J at the average overall age? Make sense? Sort of? Okay.
So these margin numbers are the same as the means from the test.
In this case, yes, because there's no covariance.
Oh.
Right?
So if there were covariates in this, then those numbers would be...
They would be different, yeah, because you've adjusted the means for the covariate. The other thing that you'll notice, if you were to go back and look at the standard errors from the univariates, these are going to be much smaller. The reason that these standard errors are going to be much smaller is because each of these predicted values are based on all 25 observations, whereas the univariate observations were based on only the number of people in that group. So what are we talking about here? We're talking about using regression to get univariate values that are more precise. You can do that with regression. This is called doing a regression with no intercept. Did I answer the question? To some degree? Okay, so the command for doing these post hoc comparisons is PW compare. This stands for pairwise comparisons. All right? So what I want to do here is pairwise, what is the factor over which I want to do my comparisons? This is the method of the comparison. So here I'm going to plug in Tukey. You can plug in some of those other things that we wrote about. And these effects in group are going to give us some other statistics as well. And we'll, after we do this, we'll stop. So it tells us up here how many groups we're comparing. Here, this gives us the same information that our margins command gave us. And here's the two-piece test. So I have, you can think of it as any two groups not sharing the same letter are different. So what that means is that AA, right, I see an A in this row and an A in this row. So groups 1 and 2 are not statistically different from each other. I don't see an A at this third row, right? So this means that groups 1 and 3 are statistically different. I see a B and B here, not bed and breakfast. This is what here. So there's no difference between here and here. Make sense? Okay. Here are the numbers associated with each of those pairwise differences. So here, this contrast is the difference between the group means. So group 2 versus group 1, it's got a p-value of 0.14. This is an adjusted p-value. Right, so here I'm looking, is this less than 0.05? Because it's done the adjustment for you. And the associated confidence interval around this difference here, right? So what do we see? We see the difference between groups 3 and group 1 is statistically significant at the 0.004 value, and the difference between the means is 2.9 units, or in this case, days. So here, these are what we refer to as adjusted p-values. Adjusted for what? They're adjusted for multiple comparisons. If I had other things in my model, these would be adjusted, well, these would be adjusted mean differences, right? Adjusted for what? The other things in the model. And here are the confidence intervals around the adjusted difference. Okay?
Standard deviation.
That's just the standard error.
No, it's not. What you're saying before, the contrast is standard deviation.
No, the contrast would be adjusted. So, because there's nothing else in the model, there's nothing to adjust for, right? But if I had other things in the model, this contrast would be the difference between the adjusted means.
What other things do you have in the model?
I could have, like in a multi-site study, for example, I might make an assumption that there's a site effect. So I could include site as a factor in the model, and that would be referred to as a block design. So by including site in the model, but not interested in its effect, I'm including another parameter in the model which should decrease the epsilon, which would then increase the relationship between my treatment and my outcome variable, and so on and so forth. But because not every site effect is the same, the expected value for treatment 1 and treatment 2 and so on, how do I compare them in any systematic fashion? Well, what is the average site effect? Plug that into the model, get an adjusted mean for treatment 1, 2, and 3, and look at the difference between the adjusted means. Make sense?
So when you report this kind of thing, you still say, like, we set alpha at 0.05
Yep.
and we adjusted for multiple comparisons
Yes.
using blah, blah,
Yes.
blah.
So in this case, to be more specific, you said you would set your experiment-wise alpha rate to be 0.05. So therefore, you can say we did 3 comparisons, but the overall alpha rate for the whole experiment was still at 0.05. By doing that, you make it more difficult for any one of these pairwise comparisons to be statistically significant. I know I said we'd be done, but there's one more thing I want to show you, and then we'll pick up on Thursday. This is what happens. Okay. This is what happens to your alpha rate if you don't do these multiple comparisons. So on the bottom here is the number of hypotheses tested. On the y-axis here is your unadjusted alpha rate. It grows exponentially. It goes up very fast. Very fast. So if you don't adjust for these multiple comparisons, the likelihood of you making a type 1 error becomes pretty significant, pretty fast. You believe you're making a decision at the 0.05 level, but you're not. And what are the consequences of that on your inference? Right? It all gets down to now that I see this in the data, what is my generalization from my sample to the population? Okay? All right. So I'm going to stop here. And where we're going to pick up on Thursday is we'll do this small example by hand, and then I'll show you how to. Then we'll take the next step, and then we'll do planned comparisons using regression in okay.